the position of X in the array. Okay, which means we need to do searching process. An element called as X will be provided. That element X, we need to check whether that X is available in the array or not. If it is available in the array, the respective index, that is what position they are speaking about. The respective index we have to tell them, determine. So we want to determine the position of X in the array. We know that X is present in the array, so that we are assuming that X is always present in the array A, and X can be present at any location. That's the next important point. X is a element which can be present at any location in the array with equal probability. How many comparisons will be required on average? So totally, how many comparisons will be required on average to find the element X? So to find the element X, what will be how many comparisons will be required on average to find the element X using linear search? So linear search is algorithm which everybody could have already known. What is linear search actually? For example, if I want to search for element called as X, if I want to search an element called as X, suppose if X is equal to 23, what I will do? I will start my process from 0th index. So I will check whether 0th index is equal to X. No, it is not equal to. That is the comparison that they are speaking about. X, okay, 0th element equal to X, right? That comparison only they are speaking about. So how many comparisons will be required on average? That is what we are going to find. So according to linear search, I will start from 0th index. I will check whether the element 0th index element is equal to X. No. So I will move to next index 1. I will check whether 1th index is equal to X. No. I will go to second index. I will check whether that value is equal to X. No. I will move to next index 3, check corresponding value equal to X. True. Now the corresponding value is equal to X. Now, when a particular index corresponding value is equal to X, I stop the process here and I say that the element is found here. So, if the element is found at third index, how many comparisons we did? For 0th index element, we took 10 and we compared it with 23. 1th index element, we took 5 and we compared it with 23. Second index 7, we took and compared it with 23. Finally, third index 23 also, we took and compared with 23 and we found it, but compared. So totally how many comparisons? 4 comparisons we did when the element is found at third index specifically. But their question is, element can be present at any location in the array with equal probability. So they are asking us to find the comparisons, that how many comparisons will be required on average. Important word, average, because they are not asking us the maximum comparison or minimum comparison. Okay, minimum comparison means 0th, if 0th index element is found, only one comparison, that's a minimum comparison. Maximum comparison means 4th index if the element is, last index if the element is found, 5, totally 5. So n comparisons we will be taking, that is the maximum, but they are asking for the average comparisons. So to find the average comparison, okay, to find the average comparison, 1 minute. To find the average comparison, first of all, we need to find how many possibilities exist. How many possibilities exist in a given array, in which, what are the possibilities of, like X can be found at index 0, first possibility. X is an element which can be found at index 1, second possibility. It can be found at index 2, third possibility. It can be found at index 3, fourth possibility. It can be found at 4, fifth possibility. So it can be present at any location. That is what the question is, right? It is present. It can be present at any location. So we have 5 different possibilities. It can be found at 5 different locations. So first location is, it can be found at 0th location. Second possibility, 1th location. Third possibility, second index. Fourth possibility, third index. Fifth possibility, fourth index. Okay, so for every possibility, we need to find the, we will need to find the comparison separately. We will find that, then we will find the average. Okay, suppose if the element X is found at index 0, how many comparison we will do? When we go to 0th index and we take the corresponding value, compare it with X, and we found that both are equal, we stop process here. Only one comparison. The 0th index element we could have taken and we could have compared it with X. So only one comparisons will be taken if the element is found at index number 0. Suppose if the element is found at index number 1, if it is found at index number 1, how many comparisons we will be making? First of all, we will start every time we will start the process from zeroth index. So zeroth index element we will take and compare it with x, which is not going to match. One comparison already made. Then we move to 1th index, we take the corresponding value and we could have compared. There the element could have matched. So how many comparison? Two comparison. Zeroth index element also compared, 1th index element also compared. Then 1th index element is same. So we stop the process there. So two comparison. So two comparison when it is coming to 1th index. Suppose if the element is found at 2nd index, what you could have done? 0th index, one comparison, 1th index, one comparison, 2nd index, one comparison, then only we found the original value x. So totally three comparison to find the value in x. Sorry, find the value in 2. So 2nd index, it will be taking three comparisons. Coming to 3rd index, how many comparisons it will be taking? 0th index, one comparison, 1th index, second comparison, 2nd index, third comparison, and finally 3rd index, fourth comparison will be happening. So there will be totally 4 comparisons starting from 0th index up to 3rd index. There is going to be totally 4 comparisons. Suppose if the element is found at 4th index, similar way, 0th index, one comparison, 1th index, second comparison, 2nd index, third comparison, 3rd index, fourth comparison, and 4th index will become 5th comparison. So totally 5 comparison you will be taking overall. So you had 5 different possibilities, and we have already found the 5 different possibility. What are the comparisons of 5 different possibility? What they are asking is average. How will you find average? Add all these possible comparisons and divide it by 5, because total number of possibility is 5. That is how you are going to find the average, right? So what I need to do is I need to add the comparison, right? So 1 plus 2 plus 3 plus 4 and then plus 5. So I'm going to add all these comparisons. I'm going to add all the comparisons from 1 to 5. I'm going to add all the comparisons. And after adding all the comparisons, I'm going to divide the entire sum divided by 5. That is the total number of possibility. Okay. So what is this 5 actually? 5 means the total number of element available in the array. The total number of element available in the array is actually equal to n. So divided by n. And similarly, what is this 5 here? 5 is also n, right? So you have to add from 1 up to, you have to add up to 5, up to n. So that's a general, we are just generalizing it. So it's like sum of all the numbers from 1 to n, natural number, all the natural number from 1 to n. There is a formula for that, am I right? The formula is n multiplied by n plus 1, n multiplied by n plus 1, the whole divided by 2. This is a formula for only this 1 plus 2 plus 3 plus 4 plus up to n. But there is also 1 divided by n, right? That divided by n, we can attach it with the denominator 2 here. So we are taking that n and we are attaching it with the denominator here. So n, 2 multiplied by n. Now, first of all, let me solve this up numerator part. Numerator part, what I'm going to do is, I'm going to do n multiplied by n, n square, n square. Then n multiplied by 1 is n, so plus n. So n square plus n, the whole divided by 2 multiplied by n. Now this 2 multiplied by n will be common to your n square also, it will be common to your n also. So let us split it into 2 different terms. So n square divided by 2n is a separate term I'm taking, plus n divided by 2n is a separate term that I'm taking. Coming to n square divided by 2n, your numerator is having n square and your denominator is having 2n. So in the numerator from n square, I'm going to take 1n off, and the denominator I'm going to take 1n. So this n will be cancelled, and here also instead of n square we'll be taking n. So it becomes n by 2. How about this term? The numerator n and the denominator n will get cancelled, so it will become 1 by 2. So what is n divided by 2 plus 1 divided by 2? It is equal to n plus 1, because the denominator is same in both the cases. So only add the numerator and divide it by 2. So the answer for this question have to be totally, generally the formula is n plus 1 the whole divided by 2 have to be the exact answer. The average comparison, how many comparisons will be required on average to find the element x using linear search? It is going to be n plus 1 the whole divided by 2. Let me take the option and also show you option of the problem question also. I will just try to show it to you. 1 minute. Just 1 minute, 1 minute. Okay, I'll just show you the option now. Option given in the exact question I will show you. And from that option, we will check whether our answer is available or not. So the option for the question is option 1, n. Option 2, n plus 1, the whole divided by 2. Option 3, 2 multiplied by n. Option 4, n square. So which one is going to be the answer for this? It's going to be n plus 1 whole divided by 2, which we found without the option, right? Option 2 is the right answer. Okay, this is how, see, maximum comparison is completely a different question. A minimum comparison is completely different. But average comparison is completely a different question. Okay, should everybody understand how this is exactly working? Everybody is okay with the logic? Do everybody is okay with the logic? Hope it's clear. I'm not confusing you. Hope it's clear. Okay, students, I'll send you the attendance link now. I'll just send you the attendance link and I will just wait for 5 minutes. You can just please respond to your attendance link. I'm just posting attendance link. You can take 5 minutes break and you can also do this. If it is maximum comparison, it will be n. If it is maximum comparison, it will be n. If it is minimum comparison, it will be 1. Just please respond to your attendance. I'm going to mute. I'm going to turn my audio off. Okay, fine. Okay, fine. Shall we move? Okay, I think let's get started. I think everybody have completed giving your attendance. I was just waiting for your attendance only to be. If anybody has missed with the attendance, I will just repost it again also for anybody's respect for anybody's. If anybody want to know like still have not given your attendance, you can just take the attendance link and you can proceed with it. Okay. So now let me just start it again with the next problem actually. So the next problem is going to be a full binary tree with n leaves. Okay, a full binary tree with n leaves contains dash node. Is this question already you have seen? A full binary tree with n leaves contains dash nodes. Have you already seen this? Has this question already been discussed? Okay, there is no. Okay, no. So now, see, see the question. Look at the question very carefully. Look at the question very carefully. A full binary tree with n leaves. With n leaves, they are asking. Okay, with n leaves, it's not the formula that we yesterday saw. 2 power h minus 1. It's not that. They're saying that a full binary tree with n leaves. What is leaf? First of all, what is leaves? Okay, I'll just give you a structure. Okay, I'll just give you a. So I'll just share you a new screen. Okay, just wait a minute. I'll just share you with the new screen. Okay, I'll just share you a new screen. Just wait 1 minute. Okay, I think hope everybody is able to see the white screen. Everybody is able to see the white screen here. Okay, the board. Okay, fine. Now, what I'll do is I'll just take a very simple binary, full binary tree. Because yesterday I think so I taught you what is full binary tree and what is the difference between full binary tree and complete binary. I hope so. I taught you for you. I taught that for you. And if yes, just please do tell me in the chat box that I have taught already about full binary tree, so that I will skip full binary tree and I will tell you only the logic for the present question. Okay, what is a full binary tree? First of all, a full binary tree is a binary tree where every node in a binary tree is going to have exactly two child. Every node in the binary tree exactly two child except the leaf node. What is the leaf node? The nodes which are available in the last level of the tree. The nodes available in the last level of the tree is called as leaf node. Okay, the node which is having null child, no child. Okay, that's what called as that is what called as leaf node. So taking this node, what I will do is, very well, yesterday I taught you about, I think yesterday I taught you about levels. The root node will belong, it belongs to level 0, and the child of the root node belongs to level 1, and the child of these two nodes belongs to level 2. Okay, fine. So this is going to be level 0. This one is going to be level 0. And this one is going to be level 1. And this one is going to be level 2. So it's level 0, level 1, and level 2. Yesterday I made it very clear that in level 0 there will be totally 2 power 0 element, 0 node will be available. In level 1 there will be 2 power 1 node available. In level number 2 there will be totally 2 power 2 node will be available. So here 2 power 0 equal to 1 node in level 0, and 2 power 1 is equal to 2 node in level 1, 2 power 2 equal to 4 node in level 2. Okay, so whatever is your level, that level should be raised to the power of 2 to get the total number of total number of node here. So for example, if you see, when you add all this node together, you will be getting the overall how many nodes will be available. So 2 power 0 plus 2 power 1 plus 2 power 2, it is equal to the total number of node available in the tree. It is equal to, what is the formula for finding the total number of node available in a full binary tree? It is 2 power h minus 1. 2 power h minus 1, where height is the tree. Height means h means height of the tree. What is the height of the tree? Height of the tree is equal to the total number of level available. So 3 level available, so the height is going to be 3. So it is equal to 2 power 3 minus 1. 2 power 3 minus 1. Now let me take only this first 2 level. Let me take only first 2 level. Only this tree, first 2 level only I am taking. When taking first 2 level, how many total node will be there in first 2 level? How to find it? 2 power 0 plus 2 power 1 element will be there totally. So first 2 levels, the total number of element will be 2 power 0 plus 2 power 1 equal to, for only 2 levels, what is the height? What is for only 2 levels? If we are taking the tree, we are not taking level 2. Just consider that this is not in the tree itself. So only level 0, level 1. What is the height? Height is 2. So which means it is going to be 2 power 2 minus 1. That is 2 power h minus 1 formula I am substituting. When I am taking only first 2 levels, level 0 and level 1. Level 0 and level 1, if I am taking, height is 2. Okay, and 2 power 0 plus 2 power 1 is equal to 2 power 2 minus 1. So if 2 power 0 plus 2 power 1 is equal to 2 power 2 minus 1, instead of this 2 power 0, instead of this 2 power 0 and instead of this 2 power 1, can I take 2 power 2 minus 1? Yes. So instead of 2 power 0 plus 2 power 1, I'm going to take 2 power 2 minus 1. From this formula, we are taking the answer and we are substituting here. Now, on the left side, what we are having? On the left side, we are having 2 power 2 minus 1 plus 2 power 2 again. Now, let me tell you what they are telling there, what they are in the question, what is given. In the question, what is given? The question is a full binary tree with n leaf contain. 1 minute. Okay, I'll just exactly paste the question here. A full binary tree with n leaves. Leaf, which is a leaf node for here? Leaf node is, these 4 nodes are called as leaf node. These 4 node only we are meaning by 2 square. So 2 square means leaf node. How many leaf node? N leaf node. So can we take this 2 power 2 is equal to n? Because 2 power 2 only leaf node, right? The count of leaf node. That count of leaf node, we will take it as n. So 2 power 2 is equal to n. So 2 power 2, another 2 power 2 is that. There also we are going to take it as equal to n. So what is this n minus 1 plus n? It is equal to 2n plus 1. 2n minus 1. 2n minus 1. So mathematically solving, this is a way of solving this mathematically and claiming that if there are n leaf in the given full binary tree, there will be totally 2n minus 1. But a straightforward explanation I will give you. In the leaf node, how many elements are there? 4 elements are there. Apart from this leaf node, how many other elements are available? 3 elements are available. If 4, this 4 is equal to n leaf node, right? So if the 4 is equal to n, then what will be 3? 3 will be equal to n minus 1. So n plus n minus 1 will be equal to 2n minus 1. That is the formula here. Okay. Suppose one more level you are introducing. Suppose one more level you are introducing. If you introduce one more level, how many elements will be there in full binary tree? For all the 4 nodes, there will be two child each. So totally there will be 8 nodes. So 8 leaf node will be there. And what are the remaining element node? 1, 2, 3, 4, 5, 6, 7. So 8 leaf node and other nodes are 7. So n leaf node plus n minus 1 other element, right? 8 and 7, n minus 1. If 8 is equal to n, then 7 will be equal to n minus 1. So for every example, if you take, if n leaf node is available, then the entire tree will be having 2n minus 1 leaf node, I mean 2n minus 1 total node it will be taking actually. I will also take you the, like I will also show you I will show you the options for this. I'll show you the option for that question. Okay. So the options are going to be, options are option 1, 2n plus 1 node. Option 2, log base 2 of n nodes. Option 3, 2n minus 1 nodes. And option 4, it is 2n nodes. Okay, so a full binary tree with n leaves contains dash node, 2n plus 1 nodes, log base 2 of n nodes, 2n minus 1 nodes, and 2n nodes. So which is going to fit our case? Third option, 2n minus 1 nodes. That is what we have also found. So is everybody is okay with the explanation? Is everybody okay with the explanation, or anything else that I want to add up here? Okay, just please go with that. Okay, is everything okay? Shall we move to the next question? Yeah, fine. There's a lot of S's coming in. So let me just continue. Okay, fine. So students, if anybody just want to learn about the tree completely, today 8 to 10 o'clock we have, by night we have 8 to 10 class we are having, where I'm explaining you with all the concepts of today. I'm just starting. We're going to start with binary heap uh, and sorry, Q binary heap and trees and graphs we are going to proceed with. So anybody who is interested, you can join there. Okay, fine. So now this is completely for pseudocode, right? I don't have much time, to discuss about logics or concepts. Okay, fine. So I will just go to the next question, and for this question, I'm going to give you some time for you to think, and for you to, find the answer of it. It's going to be a little bit, like very easy question. So that is why I'm going to give it to you. So yeah, you can take 5 minutes of time, and you can give me the answer of this. It is also based on a tree. The question is also based on tree, a very simple question. Okay, this concept already I have taught you. So yeah, okay, this is a question. This is the question. I'm going to turn my audio off. Okay. Don't think that I'm not. I mean, my voice is not audible. Okay. I'm not going to speak. I'm going to shut it down. Okay. So I'm going to turn my audio off. You just look at the question and try to answer using chat box. Please take enough time. Okay, there is a lot of people who saying with answer option no. Okay, fine. So option one, yes. The reason is because already I just simply taught you that if it is level 0, 2 power 0, level 1, 2 power 1, level 2, 2 power 2. So if level is equal to L, then it can general formula can, if level is equal to L, then you can generally say that the formula can be 2 power L, but level is starting from 0. If root is starting from level 0, but here they clearly mentioned that root is level 1. So which means we should not start from level 0. We should take this as level 1 and we should start level 1, level 2, level 3. Level 1, 2 power 0, level 2, 2 power 1, level 3, 2 power 2. So it should be 2 power level minus 1. Am I right? It should be 2 power level minus 1. So they had missed of giving level actually power the actually. So it's 2 power L minus 1. It should be the right answer because it is not root is not starting from level 0. We are starting it from level 1 actually. So that's a simple trick that we see. These are not trick and all. This is a small changes that we will do, which you will not actually listen to. You will not concentrate. Okay, they have given root is equal to level 1. This is a small change. Root is level 1. That will change the answer itself. That is going to change the answer itself. So option 3 is 2 power L and option 4 is 2 power L, but minus 1 it's a separate one. See here. 2 power L minus 1 is completely different, but here 2 power L minus 1 is completely different. Okay, but our answer is 2 power L minus 1. Okay, so this is the answer for this particular question. So we'll go see what I have planned is now we're going to discuss something about asymptotic notations like order of log n, order of n log n, order of n square, order of n. So like this we are going to learn. Okay, so we are going to learn because there are a lot of questions regarding asymptotic notation. Am I right? There are a lot of questions coming regarding asymptotic notation. It's just the time complexity and space complexity of a algorithm are related to that. Many problems are coming. So let us have a discussion of like asymptotic notation on a general. So to that I will take one more screen. I'll just take one more website actually to show you actually about asymptotic notation. 1 minute, just give me 1 minute. One minute, just give me 1 minute, please. Just give me 1 minute, please. One minute, guys. I just found it. Yeah, fine. I'll just share you the screen. I just found actually. Okay, fine. I think hope everybody is able to see. Okay, hope everybody is able to see the screen that I'm showing you. A graph like thing, Desmos. Okay, at the page, I think this page you are able to see. I think so, right? So this is a page which using which we are going to learn about. I mean, like asymptotic notation, for example, right? So what I will do is I will just include a function f of n. F of n is equal to, we're going to take the function like order of n, right? So f of n is equal to n. That's one equation, asymptotic. We're going to take all the possible time complexities and I'm going to compare how this is going to happen, right? So fine. So next I will be adding one more function, asymptotic function, which is f of n is equal to, it is going to be logarithm of n, log base 2 of n. This is second equation, log base 2 of n. Then f of n is equal to, the next one is going to be n log base 2 of n. That's the next one. Okay, it's n multiplied by log 2 base n. Next one is f of n is equal to n square, right? So I'm going to take it as n square, right? So it's scientific notation. I want to take it as it's a square, n square. Okay, it's going to be n square. So f of n is equal to n square. Now again, after this, we'll take f of n. So we have taken n, we have taken log 2 of n, n log 2 of n square. We'll take f of n is equal to, we'll take f of n is equal to 2 power n. Okay, it's going to be 2 power n. Okay, it's going to be 2 power n. And next one is, next one is, it's going to be f of n is equal to 1. Okay, I think let us order it, keep it in order. We'll take order of 1 first of all. Okay, I think it's not working. Okay, what I will do is, okay, we will just, okay, fine. So what I'm going to do here is the f of n is equal to, okay, I'm taking f of 1. And after f of 1, I'm going to place f log 2 of n. And then I'm going to place n log n, then n square, then 2n. In the same order of increasing order I've taken. Now let us look at the graph. Actually, let us look at the graph and let us understand this. How, which one is better, and which one is actually worst. You see here, here what is the color of this? Color of this is red. Can you able to see this see this red color line, which is flat, which is flat, which is not even increasing anything. It is just simply flat, order of one. Okay, f of n is equal to one. It's a simply flat equation. Can you able to see the growth actually? The blue line is little bit, like growing. It's like going upper, right? But the red line is same. So what is order of one? Order of one means with respect to what is n here? This f of n. N is the input. N is the input, and this is equation. On the right side, you have the equation. So what is f of n equal to 1 is order of 1. Order of 1 means it's constant time. Constant time means whatever your output is changing. Okay, if your output, sorry, however your input is changing, your input might be 100, your input might be 200, your input might be, like 500 or 1000 or 2000, no matter whatever it is. Okay, let us try to give here 100. You're trying to give 100, you see here, 1 minute. I think without equation, if you're giving, it's not working. It you see, yeah. So I think better to give it as f of n. It is asking a general one. Okay, f of n. So it's not at all growing. The function is not at all growing. It's just simply constant, a flat. So whatever your input is being, if you, even your input is changing, your not see your time is not going to change. That is what it is telling. The time is constant. Time is flat. So that is why I consider this to be the efficient of all. Now coming to logarithm of n, logarithm 2 of n, it's in blue color. You see here, this is that logarithm of 2. This is its logarithm of 2. See here, I'll just explain, I'll just tell you something. See here, this point, what it is, 30.03. Your input is 30.03, output is 1. Here, your input is 39.95, but your number of time taken is 1 unit. So see, even if your input is 75, whatever you go, input keep on increasing, but your value will be, but your output value will be 1. But coming here to logarithm of n, coming to a logarithm of n, if see here, this is logarithm of n line. If your output, see, if your input is 5, your number of time taken is 1 unit. If your input is 14.9, then the number of time that you're taking is 1.473. It's growing. It's growing definitely. Here it is 1 and here it is 1.476. So it's definitely increasing, but very slowly it is increasing. You see here, after here coming to 40 only, you're reaching actually 1.9. Literally you're reaching 2. Okay, coming to 50, we will check up to 50. 50 only you're reaching, coming to 50 only, what you're doing, you're reaching 2. 50, you're reaching 2. Then coming to 100, we will check for 100. 100, what you're doing in 100, you're just increasing only 2.3. Go to 200 and check. Go to 200 and check. Coming to 200, you see, still it has not reached 3, but it's slightly growing. It's growing. So I would say that logarithm of n is the next efficient asymptotic notation that we have. See, all the asymptotic notations these are all growing functions. These are all functions. We need to compare the growth of the function, how it is growing. Slowly it is growing or fastly it is growing. That is a see, that is what where the like the efficiency of asymptotic notation is. So after order of 1, I will be preferring order of logarithm of n. What is the next one? Next one is f of n, the linear one. So see here, after this order of 1 line and after logarithm of n line, the next line you will be seeing is order of n line. This is the next line. Can you able to see from this right side? You see one. You take one after the line. This is what the order of you start taking this line. This is efficient. The next line is this one. This is the next efficient line. This is the next efficient line. And so whichever line is coming first, that is going to be efficient. So first of all, order of 1, then logarithm of n. Now we are going to look after order of n. What is order of n? Order of n means it's a linear equation, right? Straight line, linear equation. You can see here, it's going in a straight line. So linearly incrementing. You see here, your x value is equal to 40 and your output is 40. Your resultant value, that is the time is also 40. When your input is 50, 45, output is also 45. When your input is 50, output is also 50. Can you able to see that both are directly proportional? When your n is incrementing linear, when your n is incrementing, your output is also incrementing in linearly, directly proportional. What is directly proportional? When input is rising, output also will be raised. When input is decreased, output also will be decreased. That is what linearity. So we call this order of n as linear time taking equation or linear growing function. So this is the next efficient equation that we have. Next line that we have, the next line that we have is this green color line. What is this green color line? N log n. So after log n, see here, here the growth is completely different. When you're 45 here, when your input is 45, output 45. But similarly for logarithm of n, if your input is 45, what will be your output? Input is 45, output is just 1.954. How much difference you have between logarithm of n and order of n? It's not a very small, it's not very small difference between logarithm of n and order of n. It is a very, very, very large difference between logarithm of n and order of n. So the first efficient one is order of 1. The next efficiency is given to order of log n. The next efficiency is given to order of n. Suppose, see, if it is even 2n also, same only. It's linear. However, it is linear. Okay, f of n is equal to 2n is also linear. 5n is also linear. 2n plus 1 is also linear. So if n is a polynomial variable which is having degree 1, which is power 1, then it is called as linear. Okay, so an equation which might have constant value also, constant value is 2, or it might have 2n plus 1. These are all constant, right? N is only responsible for the time complexity. The polynomial variable is responsible for the time complexity. So if you have any constant, then remove the constant and take only the polynomial variable. That will give you the answer. Okay, so f of n equal to n is the next, after 1 and after logarithm of n is the next efficient one. Okay, fine. After that, you have a green color line. What's that green color line? That green color line is n log n. So you see that the n log n, it is exactly starting along with log n line only it is starting with. Log n line only it is starting with. Suddenly it goes and somewhere it meets order of n line. Somewhere it meets order of n line and it is crossing it, and the growth, if you see, the growth is higher than the order of n line. Here, when your output is 40, when your input is 40, output is 40. But here, coming here, when your input is for 20, when your input is 25, your output is 42. You see here the difference. See, okay, what I will do is, here your input is 40, output 40. I will check for the same 40 here also. I'll just say, see here, your input is 40 but your output is 76, which is far better than, which is far worse than n, right? Because n input 40, output 40, but here n 40, input 40 but output 76, so taking much more long time. It's taking more long time comparing n. Okay, so we call that n log n to be the next of n. Okay, after n only you can have n log n. Okay, next, after this green line, the next line that you are seeing is the purple line. After that only you see the black line. But initially, if you see, black line is actually, see, black line is somewhere it is just like better than purple. But once it starts growing, automatically purple becomes a little bit efficient and the black becomes the best one. So what is this purple one? N square. So n square comes after n log n, and see, look at the n square growth. Actually, look at the n square growth. When your input is, I'll show you only for the input of 20. Okay, I'll just show you only for the input of 20. For input of 20, if you see, input of 20, only 50, not 20. For input of 15 itself, which is 225. There we saw previously for 40, for 45, it's just 76 for 40. But here for 15 itself, it is 225. So how much growth it is having? So n square is the equation which is far worst comparing 1 log n log n. It's more, like it's worst comparing all this one. Okay, n square itself is worst like this. Coming to 2 power 1, if you see, here the input is just 7. For input just 7, 8. Okay, around 8. Answer is 250. Output is 220. 250. It's zigzag. It's going straight. It's going very steep straight. Okay, so I would say that 2 power n is having the highest growth. It's a worst of all. It's a worst of all the time complexities that we have. So taking the common asymptotic notation that we have, for which asymptotic notation we will be getting, we will be giving the efficiency level. For order of 1, we will be giving the first efficiency. For order of 1, we will be giving the first efficiency. Okay, 1 minute. I will just get down. Okay. So look here, I will give the first preference to order of 1, this red color line, order of 1. And next I will give the next preference to order of n, order of log n line. The next precedence is given to order of n. The next efficiency is given to order of n log n. The next next time complexity is given to n square. The next final one is given to n 2 power n. So these are the time complexities where if you look at the growth, we have just made it in the ascending order. We have written it in the ascending order, which is from low to higher growth. From low growth to higher growth, we have just arranged it. So is everybody's okay with what I have conveyed now? Is everybody's okay with the explanation? Can you able to understand exactly what this asymptotic notation is all about? See, these questions are very much helpful in pseudocode because I don't know whether you have seen all the pseudocodes of Capgemini. There are pseudocodes where they will be giving you asymptotic notation. They will ask you to write it in the ascending order. They will ask you to explain it. They will ask you to order it in instead of like descending order. They will ask you which time complexity is better, which time complexity is worst. So there you will understand how this is going to happen. So how do we find the time complexity of a how do we find the time complexity of a program? See, it's like like you should understand exactly each and everything. What is it is it ascend? It is in ascending order. See, growth from the lowest growth to highest growth. That's what I'm saying. Oh, from the lowest growth to highest growth, I have written it. Okay, fine. So see, if you want to find the time complexity of some program, then you should understand when you can call something as a logarithm, when you can call something as 2 power n exponential, when can you call something as n square, when are you going, see, this 2 it's not log, okay, it's log base, log, it's not log base. Okay, fine. So now, okay, 1 minute. So things are clear. So see, what I was about to do, that's a question will give you all the F of 2 and of Okay, I think hope you're able to hear me now. Okay, I think hope you're able to hear me now. Yes. So just do tell me that do tell me if you are okay with the time complexities, right? So there is see, there is one problem given in the previous year. There are many problems asked related to time complexity. Okay, so I'll tell you a few problems. I'll tell you one question which is related to this asymptotic notation. Just 1 minute. Okay, fine. I hope you are able to hear me, right? I think hope you are able to hear me now. Just 1 minute. I'll take up this question. Actually, I'm just looking for that question to show you how this asymptotic notation is required in terms of pseudocode. Screen. Okay, there's a okay, I'll just share you with the screen now. Yes. Okay. I think hope everybody is able to see my screen. Actually, I'll just able to see my screen, and in that screen, I'll just give you the question. Actually, the question is this. The question is: consider the following functions and their complexities. I think it's. I think 1 minute. Uh, yeah. Fine. Yes, it's like n. Okay, it's n. Okay, fine. So it's the equation is given here. Okay, function following function f of n, f1 of n, and f2 of n is given. F3 of n is also given, and then see what is this 2n. This is n power 3 divided by 2. This is logarithm n. This is n log n. So when the time complexities are given like this, they are asking you which among the following options correctly represent the increasing order of asymptotic complexity of the function f1, f2, f3, and f4 respectively. So they are giving few options also. So let's just look at the concept. Look at the concept and just tell me what will be the answer. I'm just zooming it up a little bit. I'll just zoom it down, zoom it up. Okay, fine. So here few. Okay, wow. Okay, fine. Yeah, now just go ahead. I'll just give you 5 minutes of time. You can just look at this question. I can just predict the output also, right? One, fine. Okay, fine. So there are few answers, right? Okay, fine. So look at with option D, the mentioned option. Yes, by 2 is one part. Okay, sorry guys for 1 minute. Sorry for the distance. Yeah, fine. Okay, fine. I think it's audible for everybody. Yeah, fine. So everybody was like thinking about option B, option B, option C. That few people who will like look into option A, none of the mentioned option. But here the right option is actually none of the mentioned option, because I said very clearly that 3 divided by 2 is equal to 1.5. 3 divided by 2 is equal to 1.5. Okay. So what is 1.5? How you going to round it up? 1.5. 1.5 is going to be rounded off to 2 actually. So it's going to be n square. Okay, it's going to be n square. So f of n, f2 of n is going to be equal to n square. So 2n, n square, logarithm of n and n log n. Now tell me the answer. The first lesser one is going to be f3. But after log n is the next lesser one. So after log n, you have to choose, after log n, you have to choose f1, f3, then f1, then n log n will be coming, which is f4, and finally you have to go with f2, which is n square. N square is, like it is definitely greater than log n log n, and 2n. Am I right? Yes. So the order have to be f3, f1, f4, and f2, which is not available here. Okay, f3, f1, f3, f1 is itself not available here. There is no option where f3, f1 is coming first. Okay, so I would say that this is going to be none of the mentioned option. Is anybody have any conflict to? Is anybody having anything to convey here? Any doubts that you're having? Already I explained you very clearly that log n is lesser than n, and n is lesser than n log n, and n log n is lesser than n square. So only thing that I proved is n power 3 divided by 2 is equal to n square, because 3 divided by 2, 1.5. 1.5 can be rounded off to 2. So the power is going to be 2. So it is equal to, approximately, it is equal to n square. Okay. Yeah. So that's the one thing that I'm telling you. Right. Fine. So now tell me, okay, now tell me what is that you want to ask me now? What is the doubt? Okay. There are a few people, what 3 1 4 2. Yeah, it's exactly 3 1 4 2. Okay, it's exactly 3 1 4 2. There is no option with 3 1 4 2. The option is going to be none of the mentioned option. Okay, so not only like this, there are many options there. You see, there are many questions regarding asymptotic and complexities which is coming up. Okay, fine. 2n is greater than n log n, sir. No, see here. No, no, not at all. 2n is not definitely greater than n log n. That is what I said you very clearly there, in that whenever in the equation a constant value is given, take off that constant value. 2n means take it as n. It is f of n is equal to n. F of n is equal to n square. F2 or f3 of n is equal to logarithm of n. See, how will you how you are saying that? Say, okay, fine. I'll just show you here in the graph itself. I'll just show you graph. I'll just share you with the graph screen. I'll just share you with the graph screen. Just wait a minute. See, coming here to graph screen. What I will do is instead of 2n, instead of n, I will give 2n. Okay. Okay. See here. Look at here. You say that 2n is greater than log 2n, log 2 of n. Yes, of course. But you look at the growth here, you look at the growth, and after one certain point of time, 2n becomes lesser and n log n is getting greater. Can you able to look at this difference? So you cannot say that n log n, 2n is greater than n log n, because you see here, after a certain point, see here, after up to, see here, up to if the input is, I'll say here, this is a crossing point, right? Up to if the input is 50, up to if the input is 50, it is okay. But after the input is 50, just look at the growth. The growth, if you look at the growth, n log n is definitely greater than n, 2n. It's greater than 2n. Okay, so I would say that 2n is lesser, then only n log n is coming. Okay, so first of all, initially you have to give the preference to log n, then to 2n, and then to n log n, and then to n square. So this is what I was also conveying there. I think you can understand it now. Okay, I hope you understand it now, right? Fine. So the answer has to be 3421. Exactly, the answer has to be 3421, but it is not given in the option, so we have to go with none of the mentioned option. What about n cube? N cube will be greater than n square and less than 2 power n. N cube will be greater than n square and less than 2 power n. Okay, and see, you can just take this, you can take this website, desmos.com/calculator. Okay, you can go with the desmos.com/calculator. You can give your own equation and you can try which is greater equation, which is a lower equation. Okay, take this down. Okay, it's desmos.com. Okay, I'll just give you the website name. Okay, I'll just give it, give the name here. It's going to be https://www.desmos.com. It's going to be desmos.com/calculator. Calculator. Yeah, fine. So it's going to be desmos.com/calculator. Fine. Okay. I'll just share you the screen. Okay, I'll just share you a different screen. Just wait. In the new screen, you will be finding the name of the website, which you can note it down, and whenever you want, you can just go with that. Okay, any equation that you're finding, you use this website to check which equation is greater and which equation is actually smaller. Okay, which equation is greater and which equation is smaller and which equation is greater. That you can easily find with the help of the website that I have sending now. Okay, fine. Shall we go to next question? Shall we move to next question? I think we have taken enough time for doing this, so we'll do that. Okay, we'll go to the next question. Okay, fine. So the next question that I'm going to show you is a question based on recursion. So let me go with the recursion based question. This is a question. Okay, so I'll give you 5 minutes. Just work on this question and tell me what is the output for n value. I'll tell you the n value now. I'll tell you the n value. If it is n value is equal to 20. If you're calling calculate of 20, what will happen? Calculate of 20 is what you call. You call calculate of 20, what is going to be the output of this? I'll give you 5 minutes. work on this and tell me what is the exact output. Okay, I'm just I'm turning my microphone off. Okay, so no voice will be there. So just take 5 minutes and work on this question and tell me what is out. Okay, fine. So I'll just now tell you what is exactly how this is going to be calculated. First of all, I will take main memory part. Okay, I'll just take main memory part. I'll just explain you. Fine. Because of all the programs are executed inside the main memory, so that is why I'm taking main memory. Main memory means your random access memory, ram of your system. Okay, so that random access memory having actually three different parts of memory unit it is having. So three different parts inside your main memory, and the first topmost part is it is going to be it's going to be heap memory. Okay, heap memory. And the bottommost part, it is going to be code section. It's going to be code section. And the middle part is going to be stack section. Stack. So stack memory, completely for recursion, we will be using stack memory here. Okay, I'll just tell you how this is going to happen. Initially, what is that you are making? You are making a call. Whenever a function is getting called, something called as activation record will be created inside your stack memory. What is this activation record? It's like a room inside a house. Inside a room there will be multiple houses, right? So whenever you call a function, then automatically activation record, a separate room will be created for that particular call that you made. So for calculate of 20 is a call that you made. For that call, a new activation record, a new room will be created for that, actually calculate of 20. So inside this, what will happen? Inside the function, you have a variable called as n, right? So for that variable n, what will happen? One memory block will be created for that variable n inside the respective activation record. So the name of the variable is n, and the value that it is going to take is initially 20, because you're calling 20, passing 20, right? So when you're passing 20 instead of n is taking 20. Now you enter inside and you check whether n equals to 5. No, n is not equals 5. So you are not executing if part, you're coming to else part. In else part, what you're having? You are having n plus calculate of n minus 5. Okay. So remember for this recursive call. Okay, recursive call, but it's function call, right? Even though if it is recursive call, but it's a function call. I made it very clear. Whenever a function is getting called, activation record have to happen. Existing activation record we have already. How it can be deleted? It can be deleted if all the lines of the functions are properly executed. But still we have not completed all the execution. We have now come to this line only. So if we take this as line number 1, this is line number 1, this is line number 2, this is line number 3, and this is line number 4, and this is line number 5. This is line number 5. So line number 1, 2, 3, and then 4, 5. Total line number 5. 5 lines are available. Okay, fine. Now up to fourth line only we have received the now. Okay, only fourth line only we reached. So this calculate of 20 we reached up to fourth line. Fourth line we have a function call. For that function call, we will create one more activation area on top of the existing activation area, because this activation area will be deleted once you execute the close curly braces of the function. But still that's not executed, so I cannot delete it. So I will create one more activation area on top of it, and this activation area is for the call. This activation area is for the call calculate of, what is this, n minus 5, which is 20 minus 5, 15. But this function, what it is going to do, n plus, you're calling n plus calculate of n minus 5. So this is going to, what is the default n? The previous activation record n, 20. So it's going to be 20 plus, you made a calculate of 15. You made calculate of 15 call. So according to calculate of 15 call, this function is taking a variable n. So one memory block will be created for the variable n, and this variable n will be taking the new value. This is n minus 5. So 20 minus 5, 15 will be the new n value. Again you come here, 15 equals 5, not true. You come to else part, again there is a call. So what you will do, one more activation record you will create for the every function call that you are seeing. So one more call that you are doing, and in this call you are going to do n plus calculate of n minus. So what is the previous n? 15. So it is going to be 15 plus, what is a new n value? 15 minus 5 is equal to 10. So a new memory block you will be creating, and that new memory block, the memory block is actually for variable n, and the value is going to be 50 minus 5, it is going to be 10. So this activation record is for the recursive call This activation record is for the recursive call calculate of 10. This is for calculate of 10. Now, after you call calculate of 10, there will be one more activation record. There will be one more activation record created, and that activation record, what it will have do, see, because see here, you check whether 10 equals 5. No, you come to else part. You execute return n plus calculate of n minus 5, which is again a recursive call. So I created activation record. So here, what we are doing, n plus calculate of, that's very important. So what is the previous n value? 10. So 10 plus, you have to calculate of n minus 5, where 10 minus 5 equal to 5. So new memory block that you create for n, and that memory block for n should have the value 5, because it's 10 minus 5. It's going to be 5 here. Yeah, fine. Now, after you make this call, which is calculate of 5. When you call calculate of 5, where the n equals 5 is a true condition. Now, when it is true, it will return 5. So this function calculate of 5 is going to return as with it is going to return as with 10 5. So it is going to be 5 instead of this. Okay, it's going to be 5. So 5 plus 10, 15. So it will be 15 here. Okay, so it is going to return us with 5 plus 10, 15. That 15 will be returned to this previous activation record. So when this return statement is executed, automatically what will happen, this activation record will get deleted once return statement, because return statement means all the other lines will not be executed. You will directly come to the close curly braces. So activation record deleted, but n plus 10 plus 5, 15 will be taken to the next activation record. It will come here. 15 will come here. Now, after 15 is added with 15, returning 30, after, while you're returning 30, this corresponding activation record will delete and 30 will be returned. So 30 will be received here instead of this function. So 30 plus 20, 50. Before returning 50, this activation record will be deleted and 50 will be returned to the next activation record. So where the final answer will be here, it will be 50. This 50 will be returned to the calculate of 20 function. So 50 will be the answer for this. So internal part, this is I have not explaining very deeply when I'm just going with the stack now. I'm not explaining very deeply. What I'm doing is I'm telling that recursion will be using stack like this. Recursion will be using stack like this. So stack activation record will get created for every recursion call on top of the every recursion call. So when the condition becomes false, when this condition becomes true, you're not going to do recursion, which means the recursive nature is stopped. Okay, when the base condition becomes true, your condition will stop, your recursive nature will stop, and you will start deleting each and every activation record. And the return statement is the responsible for taking the answer from one activation record to another activation record. If return statement is not given, then the value 10 plus 5, 15 will not be taken into the next activation area. 15 plus 15, 30 will not be taken into the next activation area. So return statement is a highly responsible for taking the values to the next activation record. Okay, so the recursion part, you have two phases. One is creating the stack, creating the activation record is one phase, and deleting the activation record is the next phase that you are having. Okay, so this is how the answer is going to be 50 here. Okay, is it everybody okay with the answer 50? Okay, everybody have said the answer also to be 50. Everybody is okay with the explanation. Do you want me to execute this, write it as a program, and do you want me to execute it? Please do tell me. Okay, fine. So it's 10:56 now. I'm going to stop the session today of today's. Okay. So we'll be continuing the session tomorrow with the remaining pseudocodes that we will try. Okay. But and also what you're going to do is we have a session from 8 o'clock to 10 o'clock in night 8 o'clock to 10 o'clock, 8 p.m. to 10 p.m. So anybody who's interested to join with the data structures and algorithms required for pseudocode, you can better join that session also. Okay, fine. So thank you. I'm going to just close this session now. Thank you so much. Thank you.